COVID-19 has changed the way that we lead our lives in Vancouver. From restaurants to theaters to getting around on public transit, people are constantly aware of the risks to themselves and their loved ones posed by the virus. The Health Authority of Vancouver, or HAV, has been investigating potential solutions to reduce the transmission of aerosols, such as COVID-19, within indoor spaces. They've reached out to engineering student teams, like us, to assist them in this endeavor. Our engineering student team has decided to focus on reducing aerosol transmissions within buses, and we believe that we've found the ideal solution to help improve people's safety while commuting. So why did our team choose buses rather than another area of indoor aerosol spread?
Due to the large number of people and close contacts in a confined space on a bus, this mode of public transportation is susceptible to COVID-19 outbreaks. So what bus-specific mitigation strategies exist? Well, for starters, filter-based solutions are being considered on buses, but existing HVAC systems don't account for additional filters, thus requiring massive overhauls for implementation. Another strategy is to open bus windows, but they are designed primarily as an emergency exit and don't introduce enough airflow. Plexiglass panels by the driver don't specifically protect passengers either. Thus, we can see that buses need work to ensure occupants' safety. But why should we ensure that buses are safe?
Well, in addition to recognizing the health and safety risk buses pose in light of the pandemic, it is important to note how crucial buses are to our infrastructure in Vancouver. Studies have shown that if you take buses, you can better your physical and mental well-being, your wallet, the greater economy, and the environment. Despite this, the ridership of buses has decreased during the pandemic, most likely in accordance with the increase in stress and anxiety that people felt with respect to contracting the virus. So, overall, buses have many tangible benefits for the public that are not being realized due to justifiable concern of the virus spreading in buses. Our own survey of over 50 bus riders showed that approximately 90% of these respondents did not feel fully safe riding a bus at this point in time. Thus, our group selected buses as our application area in order to help regain the many benefits that they offer our population. In order to best attack the viral transmission problem on buses, our engineering team had to choose one viable bus, called a pilot site, to simulate the better part of buses in Vancouver. Our choice was the NovaBus LFS HAV Hybrid, which you may recognize as your bus if you've ever ridden the 4, 84, or 25 routes, among others. This bus is the most common diesel bus in the city, with 141 units currently running. Thus, with how common it is, it was a natural fit to simulate the better part of buses within the city of Vancouver.
So what was the next step after we had our pilot site selected? Well, now we had to figure out what exactly our priorities were when designing our solution. To do that, we had to consult with those who would be most directly impacted by it. Shown on the screen now is a comprehensive list of all the groups whose voices our team considered when designing our solution. The team prioritized these groups while considering the urgency the group would have for the project, the need for their voice in the project, and their ability to influence our project. This led to 5 groups being deemed high priority: the Health Authority of Vancouver, Coast Mountain Bus Company, TransLink, the design team, and the bus occupants. We engaged with these groups through various means, including interviews, surveys, and meetings. This allowed us to ensure that all parties will be satisfied with our final solution. Other groups were given input into the project through more passive means, whether that was through consulting their documentation or informal interviews. From these groups, we established a set of needs that our solution would satisfy, particularly pertaining to health, safety, regulations, and the environment. From these needs, the design team devised requirements for our potential solution. Breaking down the system into smaller subsystems by its function, we generated various ideas for how to complete each function, called concept fragments. After creating a wide range of over 80 concept fragments for 7 main functions, our team then began to filter through all of these ideas. Some concept fragments were filtered out because they violated a technical requirement, were physically impossible, or were beyond the technical readiness of the team. The remaining concept fragments were combined to create 14 full solution concepts. The team focused on generating a range of unique solutions, both obvious and novel. To narrow down the full concepts, we utilized a similar process of filtering out unsuitable concepts. With 7 ideas remaining, we estimated how concepts would perform relative to each other according to the 5 criteria shown here. These criteria were based solely on our stakeholder consultation. After 2 iterations of ranking concepts, the top 4 concepts were carried forward. To select the final concept, we determined the cost-benefit ratio of each solution by comparing how they would score in the various evaluation criteria outlined earlier. For reliability, we considered the perspective of different groups when evaluating the concepts, which led to one final solution: a combination of both UVC lights and increasing the airflow on the bus. UVC is a type of ultraviolet radiation which has been shown to deactivate several different viruses. Theoretically, this helps against airborne infectious diseases by decreasing your chance of inhaling an infectious particle. By placing 2 UVC disinfection units on the inside of passenger cabin air intake, this technology can be leveraged to help disinfect the air in the bus. The total cost to install these units would be approximately $2,500, and they only require 100 watts of energy to operate, which is comparable to your everyday home light bulbs. For a bus, this amounts to approximately 60 cents per day of additional fuel. They are also comparable to a standard light bulb with negligible environmental impact over their life cycle. They only need to be cleaned every 3 months and replaced after 10,000 hours of use. They would be virtually unnoticeable to passengers, providing safety without affecting their comfort levels on the bus. And what about the airflow of the bus? Well, by increasing the bus's airflow by 4 times, particles can move through the bus faster, ensuring that any infectious particle in the air will be quickly passed through the HVAC system to either be exhausted out or disinfected by the UVC lights before being recirculated back into the bus. This can be accomplished by running the bus's current HVAC system at approximately 80% of its maximum capacity. Since we would be using the existing HVAC system, no installation costs are required for this part of the solution, and the added cost of increasing the airflow is only $7.80 of additional fuel per day. So how effective is this solution? Our engineering student team developed models to figure that out. Using literature from both MIT and Harvard, we were able to calculate the viral transmission in our pilot site based on the number of people, whether they are wearing masks, the amount of fresh air entering the bus, and more. Using these models, we predict that the implementation of our proposed system will reduce the aerosol transmission by 50% from its present state.
Our team recommends 2 UV disinfection units to be installed near the passenger cabin air intake of the bus, in addition to quadrupling the airflow in the bus. A 3-phase approach to testing the solution is recommended. This process would be first testing the solution on an empty bus, then at 20% capacity, and then at full capacity, using a known amount of particles introduced and measuring the deactivation of these particles by the system. Our engineering models using current literature from Harvard and MIT predict that this change will lead to a 50% reduction in aerosol transmission in our pilot site. What this means is that using our system, if you were riding a bus at full capacity and everyone but you was infected, albeit wearing masks, you would have a 75% chance of avoiding infection. This reduction in aerosol transmission would cost only a fraction of the existing transportation budget used by TransLink, and less than $10 per day to run. In addition, it would not compromise the comfort or safety of riders, the environment, the maintainability of the bus, or any of the regulatory requirements the buses in Vancouver are required to meet. If this recommendation is not followed, and you are riding a full capacity bus with everyone infected albeit wearing masks, our model suggests that you would have double the chance of catching aerosol spread infections. In other words, your chances of catching the virus will be 50%. In addition, the added risk of catching the virus would not be justified, since our solution is not detrimental in terms of monetary cost, the comfort of the passengers, or cost to the environment. Thus, not following our recommendation purely leads to flipping a coin with bus riders' health and safety. So with our final solution better outlined, I hope that you now have a stronger understanding of our process and how we were able to develop a solution to reduce aerosol transmission of diseases on buses. With our UV and HVAC solution, every person should be able to feel safe on buses, even in these strange times. Keep safe, everyone, and thank you for watching.